Good morning, everybody. Thanks for being here, and thanks to the organizers, Josh, Nancy, and Glenn, for inviting me to talk about data integration for a dynamic urban FEW metabolism. Before I start, I also wanted to thank my colleagues Matteo Palmonari and Ningai and my student Venkat Raghavan, who contributed to this talk. So I'm going to start describing a little bit of the problem of data integration, and in particular for our urban metabolism NSF grant, introducing those topics. I'm going to give you a couple of motivating scenarios, then how I think you scale up data integration and analysis, and I will finish with some conclusions and giving you an overview of a system that we are developing at UIC. Our very interdisciplinary grant, it's called Data Integration for Urban Metabolism. It's an NSF CyberSys grant with several colleagues, including Sibyl. And you can see here the whole list. Ningai, who, as I said, contributed to these slides. This was also one of the co-PIs. You have seen a lot of this kind of diagram yesterday, but that's how our proposal went and our grant is developing. We are looking at sustainability, resilience, looking at all the flows that go into this system, looking at it from an urban metabolism point of view, considering all the inputs, energy and water, food, goods, etc., looking at outputs and closing the loop. And we are looking at this at different levels, so starting with the UIC campus, then looking at the region, and actually first looking at the city, then the region, then through our international collaborators looking at other cities as well. So when this started, the idea, when the project started, when it was proposed, the idea is that data integration will contribute to this urban metabolism idea, because we wanted to give all the power of all the data sets that the domain scientists will gather and integrate them. From my point of view, what I wanted was to have a lot of scenarios, okay, so that I could expand on the state of the art of data integration. And what is data integration? Well, very quickly is the idea of establishing meaningful connections between or among data sets, very heterogeneous data sets. But soon I discovered, that data integration is one thing, and there are many other things connected to data that need to be addressed. So one of them is data extraction. We parse and identify the data. We have to extract semantics. Without extracting the models, the schemas, we cannot really do very much. And as we are going to see, most of those data sets actually do not have those semantics. The other component of this data was the idea of data exploration, because we want to query all of our data sources and ask, okay, which data sources are about Chicago? Which data sources have temporal information? Which data sources are about something else? So we need to index in ways that we still didn't know how to, but now we know much more, all these data sources. And finally, there is also the need to perform data visualization, and also to extend this to allow users to be involved in the data integration process. So we went from data integration to several other components of data, and I'm going to talk a little bit about them. So the data integration part, this is in a way how everything started, like in 2000. For me, we had another NSF project with University of Wisconsin, and the idea was to bridge across the land use codes. And in fact, there are quite a few, because 72 counties, hundreds of cities, and so on have their own land use classification system. So it's very heterogeneous. And what did we want to do with this? Well, for example, these are the classification codes for Dane County, for Racine County. If we want to find all retail sales and service areas in these two counties, we would have to rewrite this query in terms of these two data sources. If we wanted to do it for the whole state, then we would have to rewrite this query a couple hundred times to accommodate all the counties, all the cities, etc. So you have the idea that the only way of doing this is to have mappings between all of these classification schemes, and so when we pose a query, we pose a single query that gets automatically translated. Okay, so so retail sales and service. This is a relatively easy one here, because we have to look here at the union of these two nodes. In case the query was retail sales only, of course here we have the union of the two, so we'll have to answer this with a certain uncertainty. So there will be uncertainty associated with it. So if we extend this idea of the classification of or this classification codes for land use into something that we call ontologies, and basically they organize the domains, and what we try to find is correspondences between a source and a target ontology. Okay, so, and we base those comparisons on a measure of similarity, and there are many such measures: syntactic, semantic, structural, and then also there will be an uncertainty, as I already mentioned, associated with these similarities, so these mappings between concepts. So, okay, so in our project, in fact, what we have is not only the concepts, for example, here for a city, precipitation, flu, for the other one, rainfall and influenza. We also have, so we have the values, but we also have the timestamp or time interval, and we have the location. So when we are mapping things, we have to take all of this into account, and that's where it's going to be complicated and interesting to perform all those mappings, because as far as ontology matching goes, actually we have a very good system called Agreement Maker that has won competitions exactly for testing ontology matching systems. But when you put into the equation space and time, we are into a much more general problem. So, as I said, it's not only about data integration, it's a lot about data extraction, our project. And why? Because every time we need to access a data source, a data set, many of those data sets are actually semi-structured data. So we don't have, for the most part, we don't have relational databases. We don't have unstructured data, although we do a little bit of this, as I'm going to mention next. But most of our problem has to do with HTML tables and things like this, with nested headers. So so we have to do a lot of work here. So actually the extraction of data from these tables is quite important, because there are way over 100 million tables like this on the web that have very interesting and important information that we can use freely, provided that we can extract those data. So here I'm showing you what is the challenge. So this is one of our many tables. It illustrates several things. For example, that it's a nested headers. Then we have to identify the concepts. For example, what is this table about? We have to see this table is about water stations. That's where natural language processing is actually important, because we need to parse these captions. A lot of the information turns out to be embedded in these captions. And then we have modifiers like recent, average, etc. We have values. We have units, some in the header cells, some in the data cells. We have unknown values, and we have temporal information in all kinds of formats. Okay. So the main point is we want to answer an apparently simple question, a simple query, but this query could be very difficult actually to answer, given all that we don't have that information structured to start with. But that's the objective. That's what we managed to do. And how do we do this? Well, so the idea is to assign to which of these cells exactly what are the units, what is the timestamp, etc., so that we can build a semantic network like this. And once we build this kind of graph with all what the temperature has a value, the value, what is the unit of the value, etc. And once we have this, it is relatively easy to map across the same kind of representation for the other data sources. So now we can integrate all those data sources after we do this extraction. Now the next thing is, it has to do with space and time, that I call here data harmonization. And it has to do with the heterogeneity of all our data sets. So these, the first one is about point data, then we have trajectories, then we have regions. So these are different models, so there's spatial and temporal heterogeneity. Even within the same model, we have the same kind of resolution heterogeneity that we have to bridge in order to be able to answer our queries. So here's the idea. So this is for one of the scenarios that I'm going to talk about school attendance and school districts, census tracts, census blocks, and the fact that the boundaries of these things are completely different. So if they were the same, we could aggregate or disaggregate in a more straightforward fashion, but that's not the case because they don't overlap exactly. So we have the difficulty here is when we have many-to-many relationships. So one area of one, say, census tracts correspond to many regions in the school district and vice versa. So the one school district will also overlap with several census tracts. So we have to do, for each case, really, we have to do several operations, aggregation, that could be average sum, spatial interpolation, and we may have to do disaggregation functions as well to convert everything to a format or to a semantics that actually they have the same meaning. So I'm going now to talk about a couple of motivating scenarios, food waste management. And this scenario actually was put mostly together by Ning, and the data part by the two of us did it together. But this is the idea that there is actually a pyramid of most preferred ways of using wasted food, right? So the best one is reduction at the source. Somebody mentioned it yesterday. Then it's feed the hungry people, animals, etc. And the worst possible way, which is the one that is most used, is incineration or landfill. Okay, so so there is all this hierarchy, and I'm going to talk about it a little bit later. The other one that does not necessarily have to do with with food, energy, and water, but it's turned out to be extremely similar in many ways, and it's also a social issue that I found out is also interesting, not only in the United States but also in Europe. So looks like people have this kind of problem all over. It has to do with closing public schools and what are the outcomes for students. Okay. So going back to our food waste management scenario, these numbers are really impressive. So produced but uneaten food occupies 1.4 billion hectares of land, and they represent 30% of the world's agriculture area. That was in 2007. And this has implications with water, because the water that is used for watering these crops, goes wasted, because the food goes wasted as well, right? So these are very impressive numbers. So Ning devised to start looking at this huge problem. So she devised all of these steps. And finally, the last one was to find what would be the best to try to optimize the regions of exchange of the food generation with the food consumption. And she did quite a bit of manual work. Somebody yesterday asked me, where do these data come from? Well, a lot of the data comes from manually looking through Google Maps and extracting all of this data. There's not much more that can be done regarding this. So it's not the case that you can go to a server and get all of this data, unfortunately. But anyway, so this is the zip code area at UIC, and as you see, it has an enormous number of businesses, and she performed this pilot study. Then she looked at potential users within the same area, and these are the initial results that she got. So she looked at how many, what was the quantity of generated food waste. She found out she suspected there is a missing link between supply and demand, and she tried to evaluate what is the cluster, what is the best cluster. As I said, we did a 1 mile buffer to perform these exchanges. Okay, so scaling up, we would need to consider exchanges beyond the neighborhood or each neighborhood. We would need to include even more data sets, for example, networks of distribution, and basically optimize all the solutions. So if I put this in a single slide here, we have different things to optimize. There is a domain component that has to do with that pyramid. There is a spatial and temporal components. For example, we want to maximize food freshness, and we want to maximize this neighborhood size correlation where the exchanges are performed. Okay, and so here for the second scenario, we are looking at closing, at the closing that actually happened of 47 schools in Chicago, and the potential problems, destabilize fragile neighborhoods, and affect the most vulnerable students. And this is, again, a multidimensional problem. One of the most important things would be to make sure there's a safe commute for the students, that the schools, the new schools, are close to home. So I didn't present the slide with all the data sets we considered for the food waste scenario, just because I reduced so much the presentation so that I could give it in a reasonable amount of time. But here, I kept here the data sets that we have to look at when we perform this analysis of the school closings. And there's the domain data sets, there's a community profile data sets, there's a safety data sets as well, and there's background information that have to do with geospatial ontologies, time ontologies, and so on. Okay, so all of these really need to be integrated to answer any questions, any queries that we may have, any analysis that we may want to perform on the school closings. Now, what I looked at is how scientists actually would go about trying to understand, you know, all what is happening when schools close. So, and I came across this a study by the University of Chicago about a previous school closing. So this looks like a recurring problem. And they have access actually to individual student data in their studies. They use both a temporal comparison and also a performance comparison. They establish links to poverty data from census data, but they vastly ignore other census variables and a lot of transportation data, etc. That is ignored. And we are going to talk a little bit more about this, but basically it is so hard to extend. Once you know how to use certain data sets, it's so hard to go beyond that set of data sets that you are that you usually use, right? So, so the study, these are the conclusions of the study, even with those limited data sets that they consider. And I decided to put this also in the same kind of multidimensional optimization with the three components I already mentioned. Of course, we want to maximize education outcomes. For example, we want to minimize distance between students and schools. And we want to minimize the age at which there is a match of the expected learning trajectory. Okay. Again, you know, this was interesting. This is interesting because, again, although this is a very different problem, we are matching two things: the students and the school, and the schools to where the students are assigned. So the conclusions on these scenarios are I have here 4 of them. Probably there will be more. There are many highly heterogeneous data sets, but the point is there are many and they are very heterogeneous. The people analyze this use very specific domain analytic methods. However, what scientists lack is the automatic methods for data extraction, cleaning, and integration. That's why they stick to the couple of data sets that they are comfortable with. And there is a huge lack of support for interacting with the data and the analysis of the data. And the process is basically not scalable. Okay. So what I'm going to now present is the idea of scaling up both the data integration and the analysis. Okay, so let me go straight to the slides. So on one side we have the data, on the other side we have the data analysis, and increasingly people understand that the user has to be involved in all of these processes, okay? Even if they are automatic, because the point here is that we are going to make all these processes automatic as much as possible. Still, the users need to be involved. In fact, my experience from geospatial data integration, for example, exactly the Wisconsin scenario there that I started with, is that users don't like systems that just give them the answer, okay? Just to give them all the links and they cannot verify them. They cannot intervene. So users don't like that. So there are many reasons why to allow users to intervene so that they have more control, so that they can help the integration, okay? So that we have all of these arrows here, but for example, the one there is that there are constraints. So in the sense, so the data analysis is going to dictate how you perform the integration actually, okay? So also the kind of data sets are going to dictate how you do this. For example, you cannot interpolate crime data, okay? It has no meaning if you interpolate it, just to give an example. So these things have to be completely related and again in an automatic way. And the user will have control over some of the analysis, or as much as they want to have actually, and actually on how this mapping is performed, the mapping between all the data sources. And I'm going to show a little video about later about some way of doing visual analytics to support exactly matching of ontologies. So this is the usual way. There are few known sources that the analysts are comfortable with. They integrate them just for that particular study. They do one-time analysis of all of these. So, and they use very specific visualizations when they use them. So, so the idea here is that we want actually to allow for adding data sets as needed. Okay, so instead of having, they were using 2-3 data sets. If all of a sudden they want to integrate other data sets, okay, geospatial, ontologies, transportation data that they did not integrate, they can easily add those data sets. Also, they are just using one particular analysis, type of analysis. They should have more, they should be able to switch between different kinds of analytics. So the idea expands even to the fact that that there are all these data flows, but the way you integrate actually, the way you integrate, and I called it warehouses for a better name. Warehouses are a little bit different, but the analytics actually should influence the way you perform this storage of the data in the data warehouses. And that's that feedback loop that you see there. The other idea that we have been experiencing or experimenting with in ontology matching is the idea of pay as you go. So the more effort you invest in doing ontology matching, the better the results should be. But the point is you can stop at any time your process of integration and still obtain valid results, okay? But as you go, the results should become more and more certain, more and more precise. So this is again going to the idea of the analyzing the data in the school districts and the closing of the schools. So the idea here is that you start with a certain number of data sets, then it could be that one important analysis is comparison of district schools with charter schools, which is something that people always come back to, these two things, and so that a better analysis is performed as you go along, with the idea that you can stop and still stop at any point and obtain results. And there is this need to integrate all of these data sets, and there is a mapping history about this, and there is a dynamic aspect of this, because as you add new data sets, the mappings are going to change, possibly. Okay, so we have to, so from a point of view of the big data that we perform, this is a very important and difficult subject, actually. So I'm going now to talk about the information processing and different kinds of visualization. Different kinds of methods to do it. The simplest one that was mentioned already yesterday is just overlaying visually everything, and you know, and let the domain analysts look at these things and infer. And as you know, important things can be inferred just by looking at this. Further extending this, I mentioned already visual analytics, and I'm going to show you a short video. So here, the idea is that you have an interactive interface that actually helps you in the process, in this case, of ontology matching. And you have here what is called the reference alignment or gold standard, so you actually are comparing it with the results you know you should be obtaining for all the components of the matching. But even if we don't have the reference matching, it's very important to see how the different components to this integration method vary, okay, and which ones give a strong preference to one mapping versus those that don't, and try to see what's happening, because the process that we have is actually automatic, but we allow users to, in a pay-as-you-go fashion, to actually interfere. I'm just playing it again because it went so fast. And it's just meant to be 30 seconds, but you see here the different components of the process. Okay, so this is about visualization and visual analytics, and we also, so these different mappings here, actually these different charts, I should say, are for just one of the components of the integration. Okay, so now I hope I can exit this. Yeah, so besides visualization, there's a process of query answering, and then more analytical processes. Okay, and so we categorize actually different analysis we want to do of the data as from relatively easy to much more complicated, ending with this and involving machine learning methods, for example. Okay. And I realize that I have 1.5 minutes. I'm trying to wrap this up. So I'm going to describe very briefly the Jiva prototype that we are proposing, and it's a semantic framework for geospatial and temporal data integration, visualization, and analytics. So the idea here is that it is supported by a web interface. There's a whole stack of components, and it should be extensible to address a variety of problems. And the whole thing here is that to support this principled approach, okay, that things are done not just once, but that the results can be replicated by the domain scientists. So this is the interface, and we can focus on different areas. We can specify which data sets to integrate, and there is this visualization component that I already mentioned. This is the layered architecture with several of the things that I already talked about: data extraction, ontology extraction, spatial-temporal matching, syntactic and semantic matching. So this is the ontology matching I mentioned, the application layer, the visual and visual analytics. There is a machine learning component that permeates all this lower stack here, and the data storage associated. Okay, so to summarize what I have been saying so far, is that the solutions to complex real-world scenarios like the urban metabolism and FEW go way beyond the current knowledge of data integration and analytics, by the way. One thing that is mostly missing in data integration these days is the component that has to do with geospatial and temporal. Okay, so this is vastly missing from all the research that is being performed in data integration. As I mentioned already, what we want to achieve in big data integration, or more generally big data management, is about having reproducible and principled approaches that can be used by the domain scientists. So there will be a right mix of automation and also of user intervention. And that pay-as-you-go approaches are key. So the domain scientists can integrate new data sets as they go along, refining their solution. Okay, so, and depending on how much time they have, but it should be a monotonic function in the sense that the more time and the more effort they invest in this should produce better results as they go along. So this is the end, and thank you very much.
I remember giving a short presentation to Dr. Beister some 4 years ago about the NERS department's nuclear nonproliferation program plans.